Okay, let's prove the Lipschitz continuity. And the proof will need a lot of results about compact sets and the mean value, or not a lot, but some results about compact sets and the mean value theorem, but it's actually a nice little computation. It's kind of standard analysis, so how to derive inequalities and so on. Now, first of all, f is a map to Rm, so let's denote the component functions by f1 to fm. So fi is going to from u to r for all I between 1 and m. Now, okay, with these functions, we now use the continuous differentiability of, so f is continuously differentiable. This means all the, so the partial derivatives of f are continuous, and these are, of course, component-wise these functions, and we have seen that the map to Rm is continuous if and only if the components are continuous. So the dj fi, these partial derivatives, which now go from u to r, are continuous for all I and j, so j between 1 and n. But now we have continuous functions, continuous real functions, and we restrict them to a compact set. So we have seen continuous functions on compact sets always have a maximum and minimum. So by corollary, what was it, 1177? Yeah, 77. Each dj fi has or restricted to the set K, has a minimum and a maximum. And this means if we define the following, mi, j, we define as the supremum over all x and k of the absolute value of dj of fi of x. Okay, we know that maximum minimum exists, so this means the absolute values are bounded. So this is really a finite number for all I from 1 to m and all j from 1 to n. Okay, this is where we needed the compactness. And now we need the convexity because we want to apply the mean value theorem. Since k is convex, this means we can apply the mean value theorem to any 2 points in k by theorem 1237, our mean value theorem we just discussed. For all I, first of all, for all I let me do this here. For all I between 1 and m, and for all x and y and k, and I will always already denote the components of x by x1 to xn, and y is y1 to yn in k. So we compute that for all of them there exists some, and if I is fixed, there exists some xi in k such that, so we know that fi of x minus fi of y, since we are discussing the components, these are really real functions, so we can really apply that theorem. So this is the same as the derivative of f in xi for some xi applied to y minus, x minus y, sorry. Okay. And this is the mean value theorem, and let's just put some absolute values around this. Now, this expression, if we have the components here, so x and y were with the components x1 to xn, y1 to yn, so the differences have the differences of the components, and by our formula for explicit forms for differentials, this was corollary 1217, this is the same as the absolute value of the sum from j equals 1 to n of dj fi in xi, and now the jth components, which is xj minus yj, absolute value. Now, for this we can use the standard inequalities for the absolute value. The absolute value of a sum is smaller than or equal to the sum of the absolute values. So we get this, and here we get dj fi xi, and we can also put the absolute value to both terms individually. These are all real numbers. Xj minus yj, okay. And here we can see this is bounded. There we have our estimates here. We have this is the supremum. So we can make another estimate. We can say that this is smaller than or equal to the sum j from 1 to n of mij of times xj minus yj. And we can still simplify this by saying this is smaller than or equal to mi times the sum from j equals 1 to n of xj minus yj, where mi is just the biggest of these numbers here. So mi is defined as the maximum of mi1, mi2, and so on to min. Okay, nice little inequality computation. So, yeah, let me summarize that. So, we put this here on the next blackboard. So, we have shown fi of x minus fi of y is smaller than or equal to this number mi times the sum j from 1 to n xj minus yj. And this holds for all I between 1 and m. Okay, this is an yj. This is something which looks good because this looks a bit like Lipschitz linearity, Lipschitz continuity. So it's some differences of the f, and here's some differences of the components. So this might look hopeful. Now, this is what we want to use now to get an estimate for the general, for the Euclidean norms that we need for the Lipschitz continuity. Namely, we get from this that if we take the difference f of x minus f of y, which we need for Lipschitz continuity, so this is the square root of the sum of the squares and so on, and just to make this a bit simpler, to not have to write the square root anytime, we just take the square of this. Because then, this is of course the same as, so the components are just the fi's of these and the difference of the fi's, meaning this is the sum from I equals 1 to m of fi of x minus fi of y squared. Sorry, just said something wrong. So if we insert this inequality here, this is smaller than or equal to the sum from I equals 1 to m of mi squared times now the sum j from 1 to n xj minus yj to the absolute value squared. So this sum squared. And of course this doesn't depend anymore on I, the right-hand side, so this is a big sum, and so all we need to do is to find a nice estimate for this. And this is basically a standard inequality from some standard relation that we now need here from analysis, which we haven't seen so far. Namely, if we there's a nice little trick. If we take this sum, the sum from j equals 1 to n of xj minus yj to the absolute value, this we do a little trick. Namely, it turns out this is the same as the inner product of, so the standard inner product of the vector with entries x1 minus y1 and so on to xn minus yn, the inner product with the vector which just contains 1. So this is a very unnecessarily complicated way of writing the sum. Why am I doing this? We can use the Cauchy-Schwarz inequality for this. Namely, this yields now that this is smaller than or equal to the Euclidean norm of this, which is given by the square root of the sum of from j equals 1 to n xj minus yj squared. and so this times the Euclidean norm of this vector here, and this is the norm of 1 squared plus 1 squared and so on. So this is simply the square root of the sum j from 1 to n xj minus yj squared, yes, like this, times the square root of n. So if we take the square of the sum and insert this and estimate this from above by this here, the square of this means we obtain, so from the start, f of x minus f of y in the norm squared. This is then smaller than or equal to, and now we have this first sum, I from 1 to m, mi squared. No, I am not. Mi squared times the square of this, which is now just removing the roots. So n, let's put this in front, times the sum j from 1 to n xj minus yj squared. And if we take a look at this, this is simply the Euclidean norm squared of x minus y. So this is the same as the sum I from 1 to m, mi, times n times x minus y squared. But this is good because if we take a look at this, this is just a constant. This doesn't depend on x and y. So this means we have shown that if we take roots up there, that f of x minus f of y to the norm is smaller than or equal to c times x minus y to the norm for all x, y in k. And c is then simply defined as the square root of this here, of the sum from I equals 1 to m, oh sorry, there were squares missing, sorry, mi square times n. So this is just some number which doesn't interest us, but this is just, some arbitrary random number. And so by this we get this Lipschitz condition for this constant, which means we have proven our claim of Lipschitz continuity. Sorry, I wanted to go on with the wrong thing. Next up, we will study another construction. Namely, we will now slowly focus towards higher derivatives. So we've seen the differential of a map, we have seen partial derivatives and so on. But the question is, how do we define the higher derivatives or the higher differentials? So what would be, for real functions, we have seen the second derivative as the derivative of the derivative and so on, and then we had higher and higher and higher differential derivatives. But the question is how to generalize this. In general, we have seen the differential of a map as a map to from the domain of the function to the space of linear maps. So what the really clean and sophisticated way would be to develop a bit more general rules of calculus and take a map with values in the space of linear maps and derive this again. There is a formalism for this, but this will take a few weeks and is not that too important for you, the details. So I will take a slightly shorter way of introducing higher order differentials to you. And I will start actually similarly to how I started with higher dimensional derivatives here in this chapter. Namely, I will first consider the partial derivatives. There it's easy to formulate what we could have as higher order differentials. Namely, if we take a partial derivative, this is again a map from U to Rm, to some Rm, same as the map we had originally. So the question is now, why not just take this map, this partial derivative, and differentiate this again? Take again partial derivatives and so on. And it turns out that this is kind of actually a very reasonable way to go. This is, as I said, not the most general and most abstract way, but it's totally fine for what we are going to do with this and for what you need in your physics classes. Okay, definition 1243. So let M and N as always, let U be an open subset of Rn, and assume that F from U to Rn, Rm is partially, continuously differentiable. So all partial derivatives exist and are continuous. Okay, so what's now the second order derivatives? First of all, we say that f is twice continuously differentiable if the following holds. So if the partial derivatives themselves, djf, which are again maps from U to Rm, is continuously differentiable for all j between 1 and n. Okay, and now the simple thing that we will discuss after erasing is that then the next partial derivatives, so the second order, are just the partial derivatives of these first partial derivatives. Let me write this down in detail, but first erase. I'm sorry everyone, sorry for this very sudden change of media. I have some technical difficulties, namely I'm simply out of town for a few days, and since I couldn't record everything in the lecture hall now, I have to improvise on the go. So I'm just finishing up this video here by producing a video on my tablet. So I hope this is fine for you. I will use some handwriting. I've got a pencil here in my hand, so so a virtual pencil. And I hope this will be fine. I think my handwriting is even worse here than on the blackboard. So I hope this will all be, this will work out and you will be able to follow this video. So sorry again, the next videos will of course be back on blackboard. Okay, so the last thing I defined was twice continuous differentiable, and now that we have this notion of twice continuous differentiability, we have the notion of second order partial derivatives, namely in the following way. We simply then define partial I of partial j of f. This is then simply defined, and I'm just putting some parentheses in the game here. So this is just the ith partial derivative of the map djf, so the jth partial derivative of f. And again, this is another map from U to Rm by our construction. So here, of course, we do this for all I and j between 1 and n. Okay, so we've got these mixed part or the second partial derivatives, and so twice into some directions. So I and j might be the same or they might not. And these maps, these di, dj, f are called the second order partial derivatives of the map f. Okay, and now I can even straighten out my terrible underlining. Ha, now it's straight. Wonderful. Okay, so these are the second order partial derivatives of f. Now, of course, we want to go a step further and do this for arbitrary orders. So part B of the definition, let k in n be a number with k at these 3. And now we define recursively. We assume we have already defined that something is k minus 1 times partially differentiable, continuously differentiable, and then want to say what happens if it's k times continuously differentiable. So for k equals 3, we can take the definition from A and go one step further, and then we take for k equals 4, the one for k equals 3, and so on and so on. So in general, we say that f is k times continuously differentiable. Whoops, this was rubbish. Let's do this again. Okay, continuously differentiable. Zit, wonderful. This wasn't everything. Sorry about that. No. Okay, perfect. So f is k times continuously differentiable if we know that it's k minus 1 times differentiable, continuously differentiable. Continuously differentiable. So assume we have already defined this, and as I said before, by this recursion method, we can then define it for everything. And all, oops. Sorry about that. And all partial derivatives of order k, which is what I have to define now. Of order k minus 1. Sorry about that. K minus 1. And this means all partial derivatives of the following form, which are defined iteratively. We first derive by a direction I1, then we derive by I2, and so on. No, sorry, this was... and so on to ik minus 1. So assume we have, and of course you know what's going on here. So in the first case we just have the partial derivatives of the partial derivatives, and now we iterate this game. So we could just say we assume that the second partial derivatives are again differentiable, and then we take the partial derivatives of them. Then we would have 3 indices, and so on and so on. So we get a whole so we can just iteratively construct these partial derivatives, which are all maps from U to Rm, and here I1 to ik minus 1 in 1 to n, so all possible combinations of k minus 1 partial derivatives. So let's continue here. So f is k minus 1 times continuously differentiable, and all partial derivatives of order k minus 1, so all of these, they are continuously differentiable. Then, assuming we have k minus first order derivatives, then the partial derivatives which we get, which are of the form with one index more, so di1, di2, and so on, to, no comma, sorry, okay, to dik f, which would then be defined as the partial derivative of the corresponding k minus first partial derivative. So written like this. This is actually more complicated to write down than what it actually means. So this is, I've got the laser pointer here. So this here is a k minus first partial derivative, so we assume that this is well defined. Now, we just then derive this one more time and get a map from U to Rm. And these derivatives are then called the kth order partial derivatives. Of f. Okay, so we have these partial derivatives now, and this means, so we're kind of defining continuous differentiability by this very basic notion by just referring to the partial derivatives. And so as I said before on the blackboard, this is not the most general form of differentiability, but this is fair enough. This is everything is fine for you. And so iteratively we can then construct by just deriving and deriving and deriving again all the higher partial derivatives. Okay, just some more notation. So part C. So if f is k times partially differentiable, continuously differentiable. So when we take a look at these partial derivatives here, this is a bit quite long and it's quite tedious to write them. So we use just some shorthand notation. We put, this is moving. Okay. We just take one partial symbol and just list up the directions by which we derive, just using commas here, or list them all up. So this derivative, this is of course shorthand notation for di1, di2, and so on to dikf. So this is just simplified notation here. So this is the new term. And, almost. Okay, like that. And one more bit of notation, if we derive k times by the same direction, then we can even shorten things further. Namely, we can then just write d to the power of kif. And this is what we just write for di, and so on to dif, meaning that we derive k times by the same variable. Okay, so this is the way we can define these iterated derivatives, and we can do basically the same constructions I did now for the partial derivatives by just taking directional derivatives. So again, we can iterate these constructions, so I won't go into detail on this because this is precisely the same. So analogously, if we take v1 to vk, some vectors in Rn which are non-zero, okay, then we define dv1, dv2, and so on to dvkf, defined in the same way. So these are the kth order directional derivatives. Typo. Okay, so this is, I'm not going through the construction again. So again, by iterating this construction, and it turns out by this differentiability notion, since we have seen that this, so this is all well defined if we have a continuously differentiable map. I'm not going into details on that. Now, okay, now I have to erase. No, I'm just kidding. I can do this much faster, namely by just emptying out this page. Okay, so we've introduced now the higher order partial derivatives. And now there's also some question that is kind of immediate, and this is what amounts then to a theorem. Namely, this is theorem 1244. This is the so-called Schwarzes Theorem. Schwarz, okay, let's maybe underline this a bit nicer. Okay, so Schwarzes theorem, namely the following simple question. So assume we have some, again, m, n, and n. Say we have an open subset of Rn, and we have a map from U to Rm, which is twice continuously differentiable. Differentiable. Oh, I really prefer the blackboard. This is, well, anyway, I hope this is fine. Okay, so assume the very simple point. This is twice differentiable, and assume we have some point A in U, and we want to consider the partial derivatives. Now, if we take the second partial derivatives of the form di, dj, f in A, so by two arbitrary directions, the question is now, if we use these derivatives in this order, what happens if we do this in another, in the opposite order, by just first, so on the left-hand side here, sorry, let me finish writing. So here on the left-hand side, we first derive the function by the jth component, so by xj, then by xi, and here we do it the other way around. We first derive by xi, then by xj. So the question is, what's the difference? And the good news is there is no difference. These are always equal. And this was the result of Schwarz. Then this holds for all I and j between 1 and n. Okay, so this is a statement we want to show. So the order of partial derivatives doesn't matter. This is good news because this sometimes makes things easier. Because in some situations, if the function has a particularly awkward form, it might be easier to kind of change the order of the derivation in order to obtain nicer derivatives. So, for example, if you have some functions in there, like, I don't know, the logarithm or something, which becomes a completely different functions once you derive, and depending on which derivatives comes first, this might be more or less complicated to derive in the when you want to compute them. But this is good news. So the order of derivation doesn't matter. Okay, let's prove this. So the proof starts with a nice assumption, namely we assume something without loss of generality, which looks like it would be a lot of generality lost. But let's take a look at these things that we assume, and then we realize it's not that big a loss. Now, first of all, we can assume, since partial derivatives, again, partial derivatives are derivatives of curves, which are defined component-wise. So we can basically do all the computations here for the partial derivatives for each component individually. So we just might assume that f, which maps to Rm here, which has some, the component functions here, just has one component function. So we just might assume that m is equal to 1. Okay. Next thing we want to assume, actually it doesn't matter in which directions we derive. So we can just perform this by taking I and j to be some fixed numbers, and let's take us the very simple numbers, namely I equals 1, j equals 2. And while we're at it, actually then the other variables simply don't matter, because for partial derivation in these variables, we only need to know what's happening in the first two components, and the rest stays invariant anyway. So we might as well assume we have no further variables. So we also assume that n is equal to 2. So we have a map from R2 to R and prove this for this setting and see that this generalizes a lot. Also, we might simplify our formulas a bit, and this is also, when you see later on the proof, you see that this is really no loss of generality, because in the general case it will work almost the same way. Namely, we assume that A is the origin. A is now in R2, so that A is just 0, 0, which we also write as 0 simply. So this is just 0 in R2, and of course we assume then that 0 is contained in U. Again, we could do everything I'm going to do now for arbitrary points, but this would then the formulas would get a bit messier. Now, we make the following observations. So first of all, since U is open, there is an open ball around 0, which is contained in U completely. So there exists some delta bigger than 0, let's use delta this time, such that, there exists delta so that the ball of radius 2 delta, and we will see in a second why this is useful. So the 2 delta ball around 0 is completely contained in U. Then, if we know this, one derives, if we just take the square of around 0 around the origin, which is given, so the square, which has the form minus delta delta times minus delta delta. So this particular square, this is contained in that ball actually. So this is then contained in this ball of radius 2 delta and thereby contained in U. So we have some open square, so to say. So it's an open set, which is, which looks like the inside of a square, which is part of U, and assume we have this situation here that this then holds. Now, given any fixed value of the second component y, which is in minus delta delta, we define a map as follows: gy from minus delta delta to r, which is of the form gy of x, so in the variable x, x is f of xy minus f of x0. And if you take a close look at this map, you see that, first of all, since f is continuously differentiable, each of these gy are differentiable. And simply by properties of derivatives and the definition of this, we see that this map is really the one, if you consider this in the variable x and derive it so by x, this means this would be the partial derivative in the first component here of this term, and here we would get the first partial derivative of this term. So it follows that, and by definition, gy prime of x would be equal to d1f in xy minus d1f in x0, and this holds for all x in minus delta delta. So this is what the derivative looks like. Now we want to use the mean value theorem from mathematics 1 by the mean value theorem from mathematics 1 and apply the mean value theorem to this map gy. So from mathematics 1, this was theorem 420. we know that there exists, if we want to apply the mean value theorem, and we want always apply this to an interval, and we want to take the interval spanned by containing 0 and x. So we know that there exists some psi which lies between 0 and x, but we don't know if x is smaller than 0 or bigger than 0. So we only know there exists some psi in minus delta delta, and the only thing we know is that the absolute value of psi is smaller than or equal to the absolute value of x. This is how we express that psi lies between x and 0. Let me maybe leave this page as it is and take a new one. So given such psi, such that this mean value property holds, namely such that gy of x minus gy of 0 is equal to the derivative g prime of y in g prime y in psi times x minus 0. And as we've just seen, I'm sorry about that, I just made a mistake, so I had to interrupt myself. Now, if we insert the definition of gy and this property of gy prime, so we've seen what gy prime looks like. So if we just insert this, we have that gy of x is f of xy minus f of x0, while gy of 0 is then f of 0y. And then we get minus minus, so plus f of 0, 0. And this is, so gy prime of xi, we've seen that gy prime is consists of this partial derivative, so we would get d1f in xi y minus d1f in xi 0. Okay, and this times x. Now, these points that are on the left-hand side here, so we have f of xy, f of x0, these are basically the corner points of a rectangle, and this is maybe, oops, this was bad. This is easier to memorize, so let's try to draw a rectangle here nicely, and the program is helping me at that. Yeah, okay, almost. Yeah, let's keep it at that. So we have the corner points 0, 0, x0, 0, y, and x. Y. So okay, so we basically take a look at the values of f on this rectangle. Now we've seen, so let's maybe draw a line here. Okay, just to keep this separate a bit. So we've seen that we have this equation, and the idea is now we want to apply the mean value theorem again. Namely, if we take a look at this here, at this expression here, this looks a bit like the left-hand side of the mean value theorem. And the good news is we have assumed that the map is twice differentiable. So indeed, this is a differentiable function. Namely, if we put h xi, so for fixed xi now, minus delta delta to be to r, to be h xi of y is equal to d1f xi y, this expression here, then we can use the mean value theorem again. So since f is twice continuously differentiable, h xi y is differentiable, not in y, h xi as a map is differentiable with, and by construction, you can then see that h xi prime of y, this is now simply by deriving the second component. So this is just d2, d1 f xi y for all y in minus delta delta. Okay, so this really gives us this first combination of partial derivatives, so d2, d1. And we now really want to apply the mean value theorem. So by the mean value theorem, so the same as before, the mean value theorem from mathematics 1, for each y, there exists some eta, another Greek letter, hooray, eta in minus delta delta, and again I assume that delta is between 0 and y, which means the absolute value of eta is smaller than or equal to the absolute value of y, which we have here. So such that h xi of y minus h xi of 0 is h xi prime of eta times y minus 0. And if we now rephrase this, This means we get d1f psi y minus d1f psi 0, which is just the left-hand side there, is equal to d2 d1f psi in eta, x psi eta times y. So inserting this into our above equation, so in this part where the left-hand side already appeared, we obtain that f of xy minus f of x0 minus f of 0y plus f of 0, 0 is d2 d, d2 d1f of psi eta times xy. So we have seen that since psi and eta were then chosen here depending on these points x and y, so we have, this means we have shown that for all x and y in minus delta delta, there exists some psi which depends on x and y, and now let me put this dependence explicitly here into to this psi, and we have some eta of psi and y, such that yeah, this left hand side here, oh no, I can do a trick. Let me mark this, and now I can copy this, copy, and now paste. Whoa. Okay, almost. Okay, now these tricks took me almost as long as to write it by hand, but anyway, such that this is d2 d1f on of xeta of xy and eta of xy times xy. And just take another look at this rectangle that I've drawn here. So by construction of the psi and the eta, if we now would insert the point psi eta inside this rectangle, or inside this diagram, it must lie inside the rectangle, because the absolute value of psi is smaller than or equal to the one of x, and same with eta. So psi eta would be somewhere inside the rectangle. Okay. Now, we basically started, take another look back, so we started by just, there's a pointer, okay. So by fixing y and then doing the same here for x, and then afterwards, so finding this psi, then fixing psi and introducing the second derivative. Now we could have done the same thing, precisely the same thing, with yeah, variables exchanged, so just by, oh, there's bracket missing, parenthesis missing. So we could have done precisely the same thing, but with the roles of x and y reversed. So reversing the roles of x and y, we obtain a similar thing. Namely, we can obtain in precisely the same way that for all psi, x and y in minus delta delta, there are some numbers psi tilde of xy and eta tilde of xy, such, yeah, first of all with, this is something I forgot, I'm sorry about that. So I have to mention, and this is now the crucial part here, so these two numbers are in minus delta delta, but with absolute value of psi of xy is smaller than or equal to the one of x, and absolute value of eta of xy is smaller than or equal to the one of y. And the same here. So in minus delta delta with, and same inequalities, so let's just put the same there with the tilde, such that we get the same, so again the same left hand side, so let me do my trick again, another try, almost. Okay, copy and now paste. Okay, why is this eta there anyway? Sorry. But so we could do the same thing, but now since we have reversed the roles of the variables, this time we would get d1, d2f. So the other way around, of psi tilde of xy and eta tilde of xy times xy. So we see that we have almost the same expressions here. So if we choose x and y in such a way that for x times y not equal to 0, so we choose them in such a way that not both of them are non-zero, we obtain now, since we had the same left-hand side here on both equations, that the right-hand sides coincide, and since we can just then divide by xy, we get that d1, d2, f psi of xy, eta of xy is the same as, tilde, sorry, I forgot the other way around, is the same as d2, d1, f of psi of xy, and eta of xy. Okay, these two are the same, but the problem is, of course, now that this is not the same point. If I go back to my rectangle that I've drawn here, so psi eta was somewhere inside the rectangle, and psi tilde and eta tilde are also somewhere inside the rectangle. But they might be different points a priori. But the idea is now we just do a very simple thing. We just take a limit. Namely, by taking the limit, by letting x and y converge to 0, 0 of this equation. So we obtain from, so first of all, we know that since we have inside the rectangle, so if the corners of the rectangle move towards 0, so if this whole rectangle collapses, then of course these points will also tend to 0. So we will get that limit of xy to 0 of psi of xy. This will go to 0, and in the same way the limit as xy goes to 0 goes to 0 of eta of xy is 0, and the same with the tildes. And now I can use my favorite trick again, this time for a good purpose, namely okay, no, don't move, copy and paste, namely the same with tildes. So the tildes, x tilde, xi tilde, and eta tilde will also go to 0. So now we can, the only thing we need to use is that we have the continuity then. So since f is twice continuously differentiable, and here now continuously is the crucial word, d1, d2f and d2, d1f are continuous. So if we take this equation in the first row here, so from this equation star, we get that d1, d2 of f in 0, 0 is the same as the limit as xy goes to 0 of d1, d2 f of psi tilde xy, eta tilde of xy. This is the same as the limit, by now using the equation star, of d2, d1 f of psi xy, eta of xy. And now by the same way, this is continuous, so this is the same as d2, d1 f of 0, 0, and this is what we wanted to show. So the partial derivatives commute, and since we had all these WLOGs in the beginning, this really then shows the general case, so this in fact completes the proof of the theorem of Schwarz. Okay, now this gives us the full proof, and there's one corollary of this, and this is what I will not not prove in detail, because this basically follows from Schwarzes theorem by just doing some computations between directional and partial derivatives. Namely, there's a nice consequence for the directional derivatives here. That's corollary 1244. Oh no, was it 45? I'm sorry about that. 45. Okay, so again we have Mn and N, U subset of Rn, and F from U to Rm twice continuously differentiable. Okay, and we take a point A in U. Then we know that the directional derivatives, first of all, they exist. This is from what we already know, actually, because then we know about the differentials, and we know that all the partial derivatives and all directional derivatives will be differentiable maps, so the directional derivatives must exist. And it turns out that not xy, still in the proof mode. So dv, dw, f in A is the same as dw, dv, f in A for all vw in Rn without 0. So all directional derivatives commute as well. So the proof of this I'm going to skip. I'm just writing, use basically the description of directional derivatives in terms of partial derivatives, so corollary 1217 and Schwarzes theorem that we've just seen about the partial derivative. And then you get the proof, and the whole proof is contained in the lecture notes. Okay. Now, this completes this section on basically some collection about stuff about derivatives and maps and differentials and their properties. So we've concluded here with taking second order derivatives, so d1, d2, and also directional derivatives of second order. But again, as before, we had the partial derivatives, but we saw that they were not a full answer to this notion of differentiability, and we have introduced this notion of differential. In the same way here, this second order partial differentials or higher order partial derivatives, they give us again some answer, but they are still not the full picture. They suffer the same problem basically as the partial derivatives did in the beginning. So in the next section, we want to go to higher order differentials and study this in a more general way. Again, I will not present to you the most general construction here. So, because this would take a lot more time and be analytically a lot more involved, and this is not that relevant for you. But I will introduce to you what the notion of higher order derivatives, differentials are in general, and how to construct such notions. And we will also revisit Taylor's theorem, because it turns out Taylor's theorem also has an analog for multiple variables. Okay, thank you for your attention. I'm sorry for this unusual screencast thing. I'm promising the next thing will be on the blackboard again, which I find way more convenient, or at least way nicer. But at least I could now record part of the lecture on my kitchen table. So at least that's a new experience for me. Okay, so see you in the next